Okay, can I hear me? Thank you very much for the kind introduction, Professor Kubo. I'm Takushi Shimomura now in Hiroshima University. So in the morning, I just added this picture. This is Miyajima at Hiroshima, very nice place to visit. So I'll talk about, and I'm thankful for the Sophion Bioscience, very much thankful for the Sophion Bioscience and organizing member for giving me the chance to talk about recent work. So today I will talk about the discovery and the characterization of the extracellular potassium-gated anion channels. So as you know very well, potassium ions are critical in life and cells. So their chemical gradient across cell membranes and the intracellular size is over 100 millimole. And extracellular size is less than 10 millimolar, typically around 5 millimolar or so. So, and due to this chemical gradient and the presence of the potassium-rich channel, it forms the almost basis for the resting membrane potential. And other than that, the potassium ions are important, critical as a osmoregulator or the cofactor for enzymes. So the unusual concentration of the extracellular potassium, such as hypokalemia, can lead to the periodic paralysis, arrhythmia, and epilepsy. And so such a critical disorders, critical situations. So how such potassium homeostasis is sensed and maintained in the cell? So this can be achieved. This is long believed to be achieved by the membrane proteins that transport potassium itself. So such as sodium potassium ATPase, potassium channels. So the change in the extracellular potassium concentration modulates the sodium potassium ATPase activity, or the larger intake of the potassium in the cell lead to the change in the membrane potential, leading to the some voltage-dependent signaling mechanisms. So they are the permeate ions. Then, as far as we know, so there is only one clear example for membrane proteins that recognize extracellular potassium as a ligand and convert it into the distinct signal. This is KDPD. In this case, the phosphorylation is a signal. So this is really the case for the potassium as a ligand. So the open question is that whether there is a membrane protein that recognizes extracellular potassium as a ligand and generated a distinct signal from potassium itself or not in animals or even in eukaryotes. So we found it. So that is DM-alpha. This is a anion channel, so cis loop receptor anion channel. So I will introduce the DM-alpha, what is DM-alpha, and how DM-alpha recognizes potassium. And we also found a unique mechanism among cis loop receptors that we call the mode switching mechanism. And finally, we extend such notion into the most related human gene, glycine receptor. So let me briefly introduce about ALCA. ALCA was previously reported to have a role in alkaline avoidance behavior in flies, Drosophila melanogaster, and it is expressed in Sensilia, and in the heterologous expression system, it shows a clear alkali responsive channel current increase like this. So this is alkaline activated anion channels. And we also found ALCA can be expressed in the brain nervous system, but the detailed roles are still under investigation. We don't know the physiological roles of ALCA in brain. So move on to the molecular feature. That is today's topics. So ALCA belongs to the pentameric ligand-gated ion channel superfamily, and namely cis loop receptor and 4 transmembrane helices, and they are pentamer, and they have an extracellular domain that bind to the ligand glycine in the case of the glycine receptor, and poor region. And the ALCA is alkaline activated, as I said, anion selective channel. Then among human genes, this is most homologous to the glycine receptor type 2 alpha. but it is not activated by glycine itself. So we firstly measure the DM alpha current using the Juniper's oocyte expression system. As you can see here, there is a channel current increase in response to the change in the extracellular pH to the alkaline side, activation and desensitization, as expected. So the key, this is expected, and the key point is that this measurement was performed under the standard solution containing 2 millimolar potassium, extracellular potassium. And this slide shows, this is a really serendipitous finding for us. So this slide shows how we found serendipitously the extracellular potassium dependence. Basically, we firstly thought aspartate shows an inhibitory effect on this channel, but finally noticed this is not caused by the aspartate, but caused by the potassium. That is a counter ion of the aspartate. So as you can see here, very subtle change from 2 to 3 millimolar extracellular potassium concentration show that almost 50% of channel current decrease. So we thought this might be the potassium sensitive, extracellular potassium sensitive, but still we doubted this result because this is a really subtle change, and it already contains 2 millimolar potassium. One additional 1 millimolar potassium showed a strong effect. That cannot be believed at this point. So we basically exchange a solution from 10 the extracellular potassium concentration from 0 to 10 millimolar. So now at this point, we notice at 2 millimolar, most of the channel current activities was suppressed. So this is the potassium-dependent plot, and so we just see from 2 to 3 is around there. So it seems larger, but actually the almost current was suppressed at this point. So the IC50 value is 0.65 or so. So this is near the physiological range. So we notice that alpha is a extracellular potassium inhibited anion channel. So next we investigate the cation selectivity of DM alpha. We change the cation containing the solution from potassium to other alkali metal cation. And lithium and sodium didn't show any effect, and cesium showed a so-so effect, and potassium and rubidium showed a strong effect. So this order is very much similar to the order of the potassium selectivity of the potassium channels. And calcium and magnesium didn't show any effects. So DM alpha has a strong selectivity for the inhibition of potassium ions. And next, to gain the insight into the structural basis of the potassium binding, we use the AlphaFold 3. So here is the AlphaFold 3 predicted model of DM alpha bound with potassium. So potassium bind to here, not in the orthosteric side, but rather the region where the ECD and TMD are linked. So this is not the orthosteric side, but a nice site for regulating the channel activity because the linker region, which can affect the ECD and TMD both. So the expanded view shows that all the loops connecting the ECD and TMD form the potassium binding site. And this is a more detailed view of the potassium binding site. Potassium ions are coordinated by 4 oxygen atoms of the amino acid residues that surround the potassium ion like that. And furthermore, this site seems to be supported by another strong polar interaction containing the salt bridges and hydrogen bond. This geometry might remind you of the different structure. So yes, this is similar to the channel power of the potassium channel, selectivity filter of the potassium channel. So in this plane, so potassium ion is coordinated by 4 oxygen atoms, and the distance between oxygen and the potassium are in 2.8 angstrom. This is critical because this is almost equals to the distance of the oxygen atoms of the water molecule to potassium in the hydrated state, I mean in the solution. So then potassium can enter this selectivity filter without energetic barrier, but sodium cannot do. So that is a structural basis of the potassium channel. So importantly, the distance between oxygen and potassium are 2.79 angstrom in average. So maybe the similar mechanism to the potassium channel are the structural basis of the potassium binding even in DM-alpha. Although this is behave as a ligand. But this is a model, so we have to confirm this by the different methods. So actually, we perform the mutagenesis analysis for the residue that's surrounding this part and supporting network, and all the mutation impaired completely or partly the potassium-dependent channel current decrease. So from this data, we thought that the hypothesis is correct, and maybe this is represents the structure basis for the potassium-dependent binding. So let's go back to the original question. Are there any membrane proteins that uses potassium ion as a ligand? Yes, this is DM-alpha. So I think this is, as far as we know, first example of the extracellular potassium binding protein as a ligand. So the binding of the extracellular potassium change the chloride conductance. This is a distinct signal from the potassium itself, and it occur at the near physiological concentration. And furthermore, we noticed an unusual mechanism about the potassium regulation in DM-alpha. So this is a slide. This is the data that I have already shown in the previous slide. So the alkali dependence under 2 millimolar potassium concentration. And what happened if you depleted this potassium concentration? So if this is simple antagonist, it does not affect the alkali dependence, or this is a sort of modulator, it shifts the alkali dependence. But the results are a little bit unexpected. As you can see here, channels became basically constitutively active, and lost the response to the alkali sensitivity. So as you can see here in this plot. So this data showed that the presence of the potassium is required to achieve the alkali dependence. So alkali dependence requires the presence of potassium. This is a little bit unusual regulatory mechanism, I think. So this means binding of potassium affects the extracellular domain. So then we next checked whether the potassium binding affects the TMD or not. So we measure the effect of the extracellular anion change in 2 modes. 2 modes means potassium depletion induced channel opening, or potassium presence alkali activated channel opening mode. So both are opening, but activated in a different way. And as you can see here, there are clear differences. In this mode, potassium depleted channel opening, chloride and iodide cannot be discriminated. But in this mode, chloride is more higher permeability compared with iodide. So this plot shows the ratio, conductance ratio, which means the ratio of the slopes. So as you can see here, in the potassium presence mode, chloride is the most permeable than the other anions. But in the potassium-free induced channel opening, the discrimination is more, I can say, less. So for example, iodide can permeate. And this is even true in the anion selectivity. So we can see the difference of the selectivity in the two modes. So we can say that the potassium binding affect also transmembrane domain. So and we also confirmed the effect of picrotoxin, that is a poor blocker of the anionic cis-loop receptor member. And it is also show the different effect. So from these data, we propose that there is a sort of mode switching mechanism. And the potassium binding enables the channel to be alkali sensitive and chloride preferable permeation. This indicates that POA is more restricted because the PTX also binds too tightly. And in the absence of potassium, channels are constitutively active and allowed to some extent bicarbonate also. So POA is in this case more dilated. So and potassium behaves as a mode switcher between two modes. So finally, we investigated whether such an unusual feature can be occurred even in our human genes, the more related glycine receptor or not. So this is a structural comparison between the DM alpha structure and model structure and glycine receptor alpha 2. The main chains are well aligned, but the potassium binding sites are not conserved. And as expected, of course, there is no such potassium dependence. If we exchange the extracellular solution to the potassium, there is no current, of course. Yes, but we found an interesting point. The RNA editing of a splice variant are accumulated very much close to the potassium binding site of DM alpha. So this is a little bit, how can I say, too much hypothesis, but we thought the replacement of this residue affect the putative potassium binding site and confer the potassium sensitivity to the glycine receptor. And surprisingly, that was true. So by just changing in this variant is a combination of this one and this one. And this variant showed by simply changing the extracellular solution from sodium-based one to potassium-based one, it showed the channel current increase. So it indicates the potassium sensitivity, and it occurs even without glycine. So simply potassium-dependent channel current increase occur. So in the case of DM alpha, it showed a potassium-dependent inhibition, but in this case, potassium-dependent increase occur. We don't know the exact mechanism, but maybe this is due to the type of the protein and the conformational rearrangement. So finally, we check whether our mode switching mechanism also occur in this glycine receptor variant or not. So we check the anion permeability in two modes. So without potassium, glycine activated current and the presence of potassium-induced current without glycine. And the data clearly show that bicarbonate is less permeable than the case of chloride. And but in this case, it is not so much. So there is a differences. So we concluded even in this glycine receptor alpha-2 variant, the mode switching mechanism, potassium-induced mode switching mechanism occurred. So this is summary. We found a novel extracellular potassium sensor protein from the classically investigated cis-loop receptor. That is sort of surprising. And so we also found unusual mode switching mechanism among cis-loop receptor. And this potassium-dependent modulatory mechanism exists, although weak, but in a human glycine receptor variant. So we would like to see such a potassium signaling mechanism occur in a different protein or in a different physiological roles. That further needs a further investigation. So I'd like to thank for the collaborators, Professor Minoru Saito at Tokyo Metropolitan Institute of Medical Science, who started this study. So, and I thank for the Yoshinori Suzuki at Nagoya City University, and also, of course, I thank for Professor Yoshihiro Kubo at NIPS for continuous support of this work, and I thank for this funding. Thank you very much.
Thank you very much, Takushi. Any questions? Yes.
Okay, very interesting finding. Couple of questions. One is, so the physiological concentration of potassium seems to be just a little bit above what your, dose response curve shows. So of course, under certain conditions, like when we sweat, maybe potassium concentration will fall to the range that the channels will open.
This is very much critical question. Yeah, so actually, we don't know the physiological role. You kindly say that this can be reached to this range, but we think about that in the physiological environment, whether the extracellular potassium concentration reached less than 1 millimolar or so, but we don't know yet. Maybe, okay, but this might be a really critical situation. So the extracellular concentration is typically tightly regulated from 3 to 5 millimolar or so. So I don't know when such a mechanism occur.
Second question is, you based on AlphaFold prediction, you have this putative binding site. Did you make mutations to test whether? You did.
Yeah.
Sorry.
Sorry. So I just very rapidly said. So we performed such a mutation as by the 68. These are the direct binding site, and these are the surrounding residue, like that's one or last one.
Yeah, great.
We confirm.
Okay, thanks.
Takushi, great talk. Very interesting. The mode shifting, see, do you think it's, I know you didn't look at it, but do you think it could be changing the single channel conductance and therefore different anions transport differently because of that? And who's doing it? Is it going to be Hiro or is it going to be you in Hiroshima?
Yeah, maybe I must do it. Yeah. So that is a very critical question. So we just only showed there is a mode switching mechanism, but we cannot clarify. We haven't clarified what causes this one. So change in the conductance or the change in the such a how. I don't know. We can say that change is the open probability. So to understand that, we have to perform it.
Okay, very nice. Very nice.
One last short question. One last short question.
I might be wrong, but when I heard your talk, I thought maybe potassium could be the constitutive structural element of this channel. But actually, when it exposed to alkaline state, maybe that aspartic acid gets, further ionized to get negative charge, and that no longer able to associate with potassium. It loses potassium interaction, and then it opens up. So when you completely remove potassium, there's no structural elements to keep the channel in the closed states. So it's always open, regardless of the pH. I think that would be the better interpretation of your data.
Thank you so much. You said this one, aspartate. Yeah, that's a really critical point. And basically, we check it But I think this is not the pH sensor. We have already checked it. So yeah, that's a really critical point that we really want to know. So the relationship, the potassium binding and the pH dependence. Yeah, thank you for the comment.
Okay, I understand you have questions, but from interest of time, please ask later. Okay, I'd like to close. Thank you, Takushi.
Thank you very much.